All right, in question number 6 on the 11.3 worksheet, we're told that distance, rate, and time are related by the familiar equation distance equals rate times time, and I've just abbreviated that here. Part A says, if we hold the distance constant, how are the rate and the time related, directly or inversely? All right, so in this equation here, it's the distance, the thing on the left here, that is constant. And since we're taking the product of the rate and the time, and that always has to come out to be some fixed value, we're saying, well, we have a constant product. And so that indicates that R and T vary inversely. Okay, I just want to point out that this is really exactly the same thing we saw in problem number 1 on the 11.3 worksheet, where we were driving from Spokane to some city 72 miles away, right? That distance was fixed, and we could change our speed, or in other words, the rate of our car, and that then determined the travel time. And there we saw that the speed and the travel time were inversely related, okay? So that's exactly the same thing we see here. All right, part B says, if our travel time is fixed and we increase our rate by 35%, by what percentage does our distance change? All right, so now what we're doing is we're fixing some drive time. The t here now is constant. So let's say we decide, okay, I'm going to drive for 2 hours, okay? Now, if I go ahead and increase our rate by 35%, so I'm going to speed up, right? If I'm going to drive still for 2 hours, I would then expect, right, my distance would increase, right, because I'm going faster. All right, so how do I actually determine the actual percentage by which our distance will increase? Well, we saw this sort of thing in the 11.2 worksheet in question number 3, where we talked about areas of triangles there. Here, if we're going to increase our rate by 35%, okay, we're going to take 100% of R, and then we're going to tack on 35% of R. So in other words, we're going to take 135% of R, which of course translates to 1.35 times R. Okay, so over here, what I'm going to do is I'm going to multiply the R by 1.35. That's going to increase the original rate by 35%. Now, the travel time t is constant. I can't mess with that. So in order to balance the equation, I'm then going to have to multiply the left side by that same amount. Right? The distance is also going to have to be multiplied by this. These two effects are really going to just cancel out. But what we're saying is, for an increased rate, we're going to see an increased distance, and in fact that increase would be the same. So here we can say that the distance will also increase by 35%. Right? A multiplication by 1.35 is just giving rise to an increase of 35%. Okay? Alright, so then on to C, it says, if our distance is constant and we increase our rate by 35%, by what percentage does our travel time change? Okay? This problem is, I think, deceptively difficult. Okay, it sounds basically like just a rehash of part B. I'm going to put a little star next to it. As we're going to see here, this does take a little bit more care. Here, one difference, of course, is that we're now going to fix the distance as opposed to the time like we did in part B. So this part here, the D on the left, is our constant. And what we said in part A, right, that would then imply that the rate and the time would vary inversely, so same kind of thing here. And then coming over here, right, if we're going to increase our rate by 35%, well, just as we did in part B, that's going to correspond to a multiplication of our rate by 1.35, right? So I'm going to go ahead and multiply, that's a little dark here, we're going to go ahead and multiply the rate by 1.35. So now what am I going to have to do to the time? Well, here the idea is, right, let's say I'm driving to a city, say 72 miles away. If I increase my rate, so I'm going faster, I'm going to get there in a shorter amount of time, right? So what exactly is the percentage decrease then in my travel time? Well, here's the deal, right? The left side is fixed. So if I multiply the r by 1.35, I'm going to have to counteract that with a division by 1.35. So these two effects would cancel out. Okay? Now here's the tricky part. Okay? What does it mean to divide a quantity, say time in this instance, by 1.35? I want to understand this as a percentage decrease. Okay? So off to the side here, let's make a little note here and say, all right, well, what is 1 divided by 1.35? Well, at least approximately, around here a bit, this is equal to 0.74. Okay, so this little bit right here, the multiplication of time by 1 over 1.35 is the same thing as doing 0.74 times the travel time t. So in other words, right, what I'm doing is I'm multiplying t by 0.74, or in other words, I'm going to take 74% of t, right? So I'm decreasing t, right? I'm only taking 74% of that original t value. So what is this as a percentage decrease, right? Well, 100% of t is just t itself, and I'm only taking 74% of t now for the new travel time. So in essence, I've taken off what? Well, 100% minus 74%. This is going to correspond to a roughly 26% decrease. Okay, so here's the punchline for part C. Again, pretty tricky here, right? Time, the travel time will decrease by 26%. Okay, so give this one, I think, another view. This one is, again, a little more challenging. All right, great. That'll do it.